The last type of network topology we'll be discussing is the physical cellular topology. Cellular topology is also called wireless topology. The network is made up of circular areas called cells. These cells are serviced by a central station or hub. Network communication is available through the use of radio signals. These signals carry data from stations within the cell to the hub. The hub then routes data to devices in other cells by using their hubs. Installation of a cellular network topology is different than from any other topology. Finding a suitable hub location is probably the most difficult. If the cellular network will cover a wide area, it may be hard to find the property to acquire for central hub placement. If the cellular network will be local, we should make sure that there is nothing obstructing between the nodes and the hubs. Troubleshooting depends on how the network has been constructed. Node-to-hub troubleshooting is easy because each device interacts with the hub independently. If we have central hub failure, all devices in that cell are affected. Advantages include easy installation and troubleshooting, and reconfiguration is not a major concern. The disadvantages include the failure of one hub bringing down all devices that depend on it, and also security. The third topic that the physical layer is involved with is called signaling. Signaling is the way network data is transmitted across the medium. Signaling involves using electrical energy for communication. Network data, or the bits and bytes, must be represented in a way so that the sender can create a message and the receiver can understand it. This is done by a process called encoding. Encoding alters the original signal in a way that allows it to represent data. Information to be communicated can exist in two forms, analog or digital. Analog information changes constantly. An analog clock is a good example of this. It is always changing the time because the second hand never stops. Digital information is made up of discrete or hidden states. This can be on or off, or 1 or 0. A digital clock doesn't show the different variations of time between the minutes. It's either 1 o'clock or 1:01. Two signaling methods that correspond to the two types of data we just described are digital signaling and analog signaling. Most computer networks use digital signaling. Methods of encoding data in a digital signal are called encoding schemes. Two categories of encoding schemes are current stated encoding and state transition encoding. In current state encoding, data is encoded by the presence or absence of a signal. In state transition encoding, the data is represented by a change in the signal. Some encoding schemes that use current state encoding include unipolar, polar, return to zero, and biphase. Encoding schemes that use state transition encoding include bipolar alternate mark inversion, non-return to zero, Manchester, differential Manchester, and biphase space. Analog signaling is performed using electromagnetic waves that are constantly changing. Electromagnetic waveforms are measured by using three characteristics: amplitude, frequency, and phase. The amplitude characteristic measures the strength of the signal or the height of the wave. The measurement is expressed in volts for electrical potential, amps for electrical current, watts for electrical power, and decibels. Decibels indicate the ratio between the power of two signals. The frequency characteristic is the amount of time that it takes for a wave to complete one cycle. A good example is if a signal takes 1 second to go from high to low and then back to high, or one cycle, the frequency of the wave would be 1. This characteristic is measured in hertz, or cycles per second. The phase characteristic differs from amplitude or frequency in that it needs more than one wave. Phase is the relative state of one wave when timing begins, which is relative to another. This other wave is known as a reference wave. This characteristic is measured in degrees.